I wanted to step back and say something about capacitors and energy storage, and something that the book talks a little bit about, which I'm sure that you can deal with and make sense of. The book shows you that the energy stored in a capacitor is Q squared over 2C. You can do that just by integrating as you add charge to a capacitor. As you add charge to a capacitor, the charge gets bigger, but so does, so that's Q, but so does the voltage difference, and so it costs you more energy when the voltage difference gets larger to charge it up even more. So the Q over C is the voltage difference part, the Q is the charge part, and the charge times Q over C is Q squared over C. The 1/2 comes because Q over C is the total voltage, and you start out at 0 voltage when you're charging a capacitor, and you end up with voltage of Q over C, and so on average you're half of Q over C. So when you integrate it, you end up with that 1/2. Energy stored in a capacitor is that. So a reasonable kind of final exam question, this might be an easy one, but a reasonable one. Find the capacitance of those two plates. Show that the energy stored in the capacitor is equal to the energy in the electric field. Energy in the electric field is something the book talks about. I am not going to ask you this later, but I thought you might as well at least see it because the ideas are not hard to deal with. The energy density in an electric field depends on E squared, the square of the electric field. Energy stored in the capacitor is something that we've at least talked about, if not actually calculated, but you've calculated it, I think. So find the capacitance. Well, how do you find the capacitance? I'm jumping ahead here. How do you find the capacitance? Capacitance is the amount of charge you can store. This is essentially a definition at this point. The amount of charge you can store divided by the voltage difference it took to put that total charge Q on there. So it's a little like heat capacity, which is how much heat you put in divided by the temperature difference that it caused. So this is how much charge you can put on divided by the voltage difference that you caused. If you put on more charge, you'd get a bigger voltage difference. You'd have a bigger voltage difference, but that would end up with the same capacitance. So how do you find, well, Q is just the charge. If you want to find capacitance, I should call this one 1, 2, and 3. Capacitance is Q over delta V. So how do you find delta V? Well, you know how to find delta V. You integrate the electric field. So I can find C if I could find delta V. I could find delta V if I could find E. How do I find E? In a lot of situations, use Gauss's law. In particular, for these two plates, say there's a total charge Q. Charge per unit area is the total charge divided by the area on the plate, Q over A. Down here is a negatively charged plate. But if I want the electric field here, I want the electric flux through this space through that face of a cylinder, if the cylinder has area A, say, the face of the cylinder, there's no electric field out here because the plus and the minus plates cancel. And so the only electric field is in the center here, in between the two plates. And so Gauss tells me that E dot dA is E times the area of that face. The electric field in between the plates times the area of the face is equal to Q enclosed. The charge enclosed is the charge per unit area, Q over capital A. That's the charge per unit area, times the area of that cylinder. That's the amount of the charge that's inside that cylinder. So times the area of the cylinder face. And then divided by E0. So the area of the cylinder face cancels, and I find out that the field in between is Q over A E0 by Gauss's law. The field in between the two plates. How do I get delta V? Well, we did some of that last time.
Question?
Yeah.
You know it's E times A because electric field is perpendicular to the surface at all points.
Yeah, the electric, by symmetry for this giant plate, the electric field is perpendicular to that surface, the bottom surface. And it's constant over that bottom surface. So I don't have to worry about integrating it changing as I go around the area. So it comes out of the integral, and then it's just E times the integration of the area, which is just the area of the face. From that electric field, Q over A E0, that's just a constant in between those two plates. And so if I what do I want to call that? Let's just call that dy from 0 to d, just in between those two plates. If I call this vertical axis the y direction, then the electric field is only non-zero in between those two plates. So from y equals d, from y equals 0 to y equals d, I don't know, I got to be careful about signs here, but I'm not going to be very careful about signs. This integration over the area is just d. Over the length is just d, the distance between them. And so delta V is Q times d over A E0. And so the capacitance is Q over delta V. If I divide this delta V into Q, what do I get? A E0 over D for the capacitance of this capacitor. What I asked in the problem, I don't want to do right now. Maybe I'll do it next time or maybe not. The reason I don't want to do that right now is that I have another capacitor for you.